Post-medical imaging processing. Image post-processing belongs to the domain of digital image processing, which simply the processing of an image using digital computer. The major goal of digital imaging is to alter or change an image to enhance diagnostic interpretation. For example, images can be post-processed for the purpose of image analysis, image restoration, image enhancement, and image compression. These operations are intended to transform an input image into an output image suit the viewing needs of the observer in making diagnosis. In addition, these operations can be also used in digital photography and have become available in commercial image processing software. Introduction. The advantage of digital imagery is that it allows us to manipulate the digital pixel values in the image. Even after the geometric corrections, image may still not be optimized for visual interpretation. So an image enhancement is basically anything that makes it easier or better to visually interpret. An enhancement is performed for a specific application as well. So our topic for today is one of an image enhancement, which is also known as filtering. Filtering is a technique used for modifying or enhancing an image, like highlight certain features or remove other features. The term convolution means applying filters to an image. Image filtering includes smoothing, sharpening, and edge enhancement or noise removal. So basically, there are two types of filters, the spatial domain filters and the frequency domain filters. The first type of filter, which is the spatial domain filter, it is a technique used directly on the pixels of an image. It is just moving the filter mask from point to point in an image. This mask is moved on the image such that the center of the mask traverses all image pixels. The filter mask may be a 3x3 mask or 5x5 mask or to be 7x7 mask. So there are two general classifications of spatial domain filter. First is smoothing spatial filter. Smoothing filter is used for blurring and noise reduction in the image. Blurring is used as pre-processing such as removal of small detail from image. Noise reduction is blurring with linear and nonlinear filter. There are also types of smoothing spatial filter. Number 1. Linear filter, or also known as mean filter. It simply filters the average of the pixels contained in the neighborhood of the filter mask. The idea is replacing the value of every pixel in an image by the average of gray levels in the neighborhood defined by the filter mask. Another type of smoothing spatial filter is the order statistic filter, or also known as nonlinear filter. It is based on the ordering pixels contained in the image area encompassed by the filter. It replaces the value of the center pixels with a value determined by ranking result, so edges are better preserved in this filtering. Next is the types of nonlinear filter. First is the median filter. This filter ordering the pixels by replacing the value of the center pixel with the value of rank list. Second, max filter. This is used for finding the brightest point of an image. Last is the min filter. Opposite of max, that is to find the dull points of an image. The second general classification of spatial domain filter is the sharpening spatial filter. It is also known as derivative filter. The purpose of sharpening spatial filter is just the opposite of the smoothing spatial filter. Its main focus is on the removal of blurring and highlight the edges. As you can see in the picture, ang edges sa second picture is clearer than the original one. Sama na siya in sharpening spatial filter. So another type of filter, which is the frequency domain filters, are used for smoothing and sharpening of an image by removal of high and low frequency components. There are three types of frequency domain filters. First, low pass filter. It is used to smoothing the image by attenuating high frequency components and preserving low frequency components. Second is high pass filter. It is used to sharpen image by attenuating low frequency components and preserving high frequency components. Last was the band pass filter. Band pass removes the very low frequency and very high frequency components. That means it keeps the moderate range band of frequencies. It is used to enhance edges while reducing the noise at the same time. Thank you.
Contraction and enhancement. Image enhancement is the procedure of improving the quality and information content of original data before processing. Common practices includes contrast enhancement, spatial filtering, density slicing, and FCC. Contrast enhancement or stretching is performed by linear transformation expanding the original range of gray level. Spatial filtering improves the naturally occurring linear features like fault, shear zones, and lineaments. Density slicing converts the continuous gray tone range into a series of density intervals marked by a separate color or symbol to represent different features. FCC or false color composites. It is commonly used in remote sensing. Remote sensing provides information about objects at or near the surface of the Earth and atmosphere based on radiation reflected or emitted from those objects. FCC is standardized because it gives maximum identical information of the objects on Earth and satisfies all users. Example in standardized FCC is when vegetation looks red because vegetation is very reflective in NIR and the color applied is red. Why image enhancement? First, can't distinguish between tissues. The nature of the physiological system under investigation and the procedures used in imaging may diminish the contrast and the visibility of details. 2. Data is too noisy for computer algorithms to perform well. Medical images are often deteriorated by noise due to various sources of interference and other phenomena that affects the measurement process in imaging and data acquisition system. Third, imaging artifacts interfere with visualization or computer processing. How to enhance image? First, increase the contrast. Second, remove the noise. Third, emphasize edges, either edge boost or unsharp masking. Lastly, modify shapes. Image enhancement techniques ranges from linear to non-linear, from fixed to adaptive, and from pixel-based to multi-scale methods. So here is the example of contrast enhancement by histogram equalization. Here is an example of enhancement by adaptive wavelength shrinkage denoising. And here is an example of enhancement by adaptive filtering, noise or speckle reduction.
Registration is a special transform that maps points from one image to corresponding points in another image. It is defined as a process that overlays two or more images from various imaging equipment or sensors, taken at different times and angles, or from the same scene to geometrically align the image for analysis. So there are 4 examples for registration transformation. First is the original to rigid, original to similarity, original to affine, and original to deformable. So the rigid transform, it can register objects that are related by rotation and translation. For example, if you are registering images of a patient's bones, you can often assume that a rigid transform is sufficient to align this structure. Second is the similarity. One or more rigid transformations, reflection, rotation, and translation followed by adulation. When a figure is transformed by some similarity transformation, an image is created similarly to the original figure. In other words, two figures are similar if a similarity transformation will carry the first figure to the second figure. Third is the affine. It is a linear mapping method that preserves points, straight lines, and planes. Sets of parallel lines remain parallel after an affine transformation. This technique is used to correct for geometric distortions or deformation that occurs with non-ideal camera angles. Next is the deformable. It involves estimating the geometric transformation between two images to map them onto a common coordinate system. The process is deformable because the estimated transformation does not include any rigid transformation but also deformation. Registration criteria. First is the landmark base, features selected by the user. The segmentation based, rigidly or deformably aligned binary structures. Last is the intensity based, minimize intensity difference over entire image. Special transformation. The rigid, affine, and deformable. Rigid, rotations and translations. For the affine, also skew and scaling. Deformable, free-form mapping. The registration framework pieces. Two input images, fixed and moving. The metric, optimizer, and the interpolator. The metric determines the fitness of the current registration iteration. The optimizer adjusts the transform in an attempt to improve the metric. And the interpolator applies transform to image and computes subpixel values. Classification is done on the basis of extracted features by classifier. There are two main approaches of pattern recognition for feature extraction and classification based on the type of features. First is the statistical classifier, and second is the syntactic classifier. In case of statistical approach, pattern or texture is defined by a set of statistically extracted features represented as vector in multi-dimensional feature space. The statistical features could be based on first order, second order, or higher order statistics of gray level of an image. The feature vector so generated from patterns is assigned to their specific class by probabilistic or deterministic decision algorithm. In case of syntactic approach, texture is defined by texture primitives, which are spatially organized according to placement rules to generate complete pattern. In syntactic pattern recognition, a formal analogy is drawn between the structural pattern and the syntax of language. Segmentation. Segmentation is the process dividing an image into regions with similar properties such as gray level, color, texture, brightness, and contrast. The rule of segmentation is to subdivide the objects in an image. In case of medical image segmentation, the aim is to first, study anatomical structure. Second, identify region of interest. For example, locate tumor, lesion, and other abnormalities. Third, measure tissue volume to measure growth of tumor, also decrease in size of tumor with treatment. Fourth, help in treatment planning prior to radiation therapy in radiation dose calculation. So there are techniques for the segmentation of images. These are the pixel-based segmentation, edge-based segmentation, region-based segmentation, and the hybrid algorithm. In the pixel-based segmentation, it includes thresholding, adaptive thresholding, and clustering. For the edge-based segmentation, it includes live wire segmentation, snake algorithm, active contour algorithm. For the region-based segmentation, it includes agglomerative algorithm and the divisive algorithm.
Medical image display visualization and presentation. Modern medical imaging modalities such as multi-detector computed tomography, magnetic resonance imaging, and positron emission tomography. Fused with CT generate large data sets that are difficult and time-consuming to review by using the standard axial section view. Advanced image visualization and data navigation techniques, adapted successfully in other fields, may aid radiologists in their daily tasks. An understanding of radiologists' visual and interpretive behaviors, explored in conjunction with the capabilities of innovative advanced technologies, may provide useful new paradigms for interpreting results from medical imaging examinations. Image displaying. Image display is used for displaying digital image data into a visual color image as a tool for real-time man-machine interface. An image display system consists of a frame buffer, lookup table, DA converter, and a display. So, what is frame buffer? Frame buffer is an image memory to allow high-speed reading of digital image data. The size of the image memory is usually 512 by 512 to 2048 by 2048 picture element. The primary roles of frame buffer are the storage, conditioning, and output of the video signals that drive the display device. The industry standard for color application allocates 8 bits of intensity control for each display primary of approximately 16.8 million discretely addressable colors. The amount of the memory required to hold the image depends primarily on the resolution of the screen image and the color depth. The match between the sampled values and human color sensitivity is imperfect. However, not all display colors can be discriminated from one another, and many colors that differ by the single bit in their digital representation are significantly above threshold discriminability of the eye. The result in various types of color artifacts such as contouring artifacts and shaded graphics. Lookup table. Lookup table is a preset function to enable conversion from an input signal to an output signal in real time. Before the advent of computers, lookup tables of values were used to speed up hand calculations of complex functions such as trigonometry, logarithms, and statistical density function. Linear function, contrast enhancement function, gamma function, log function, etc. are mostly used in lookup table. DA converter. DA converter, or digital to analog converter, converts digital image data in a frame buffer to an analog video signal. So, DA converters form an important link between analog and digital world, and let computers talk to equipments that usually uses analog signals by converting a binary count to a proportional discrete voltage level. Display. The most prominent part of a computer is the display system that is responsible for graphic design. So there are several types of display: CRT, liquid crystal display, plasma display. So we will go start with cathode ray tube, or CRT. CRT is the image on a CRT display is created by firing electrons from the back of the tube of the phosphorus located towards the front of the display. So for the picture there, as you can see, those are the parts of cathode ray tube, or CRT. So there is a grid, cathode, focusing anode, acceleration anodes, Y plates, electron beam, X plates, and fluorescent. So basically, there are two types of CRTs: raster scan type and random scan type. The main difference between the two is the technique with which the image is generated on the phosphorus-coated CRT screen. So what is raster scan type? Raster scan type, the electron beam sweeps the entire screen from left to right, top to bottom, in the same fashion as we write on a notebook by word by word. Random scan type is the electron beam is directly straight way to the particular points on the screen where the image has to be pronounced. Liquid crystal display LCD. LCD consists of a layer of liquid crystal sandwiched between two polarized plates. So in the picture, there is the layer of the liquid crystal. So there is a electrodes, polarizing filter, light source, liquid crystal, electrodes, color filter, polarizing filter, display surface. The polarized are aligned perpendicular to each other. So the light incident on the first polarized will be blocked by the second. The intersection of the two conductors defines a pixel position. The liquid crystal material is made up of long rod-shaped crystalline molecules containing cyanobephenylnyl units. The individual polar molecules in nematic LC layer are normally arranged in spiral fashion. In a color LCD, there are layers of 3 liquid crystal panel one on top of other. Each one is filled with color. So these are red, green, or blue liquid crystals. Advantages of the 3 layers. It helps create as many as screen pixels as intersection. It has high resolution panels. Each pixel comprises 3 color cells or sub-pixel element. Comparison between LCD and CRT. So the image painting operation and LCD panel is different from CRT. Both are raster scan. Plasma display. Thin vertical strips of conductor run across one plate while horizontal conductors run up and down the other plate. How does it work? It works by applying high voltage to a pair of horizontal and vertical conductors. A small section of gas at the intersection of the conductors break down into glowing plasma of electrons and ions. In the array of a gas bulbs, each one can be set to an on state or off state by adjusting the voltage of the pair of conductor. Advantages. 1 is excellent brightness, 2 high contrast, 3 huge scalability. Display workstation and other tools. Display workstation. A workstation includes communication network, hardware and software, a local database, a display monitor system, resource management, and processing software. The primary diagnostic workstation also has access to the PAC server database for retrieving images in an on-demand fashion. There are 4 types of display workstation categorized by their resolution. 1. High resolution has 2.5 by 2K liquid crystal display or LCD for primary diagnosis at the radiology department. 2. Medium resolution has 2000 by 1600 or 1600 by 1K LCD for primary diagnosis of sectional images and at the hospital wards. 3. Precision desktop workstation has 1K by 768 LCD. And 4. Hard copy workstation for printing images on film or paper. Image retrieving. Image retrievals takes place at the same workstation that are connected to the archive system through the communication network. Retrieval requests are issued to the archive server by the display workstation using DCOM query retriever or QR system service class via TCP or IP network protocols on a client or service basis. In the retrieval operation, the archive server serves as a QRSCP processing query and retrieval requests it received from the display workstation. Request images are retrieved from the storage subsystem by the archive server and distributed to the destination display workstation with use of DCOM storage service class. So as you can see in the figure 1.1, this is the example of a picture archiving and communication system diagnostic workstation displaying a magnetic resonance in the brain exam. In the figure 1.2, this is the example of a picture archiving and communication system diagnostic workstation displaying a computed radiographic chest exam. So there are other tools of display workstation. So first, case preparation. Case preparation is an accumulation of all relevant images and information belonging to a patient's examination. Second, case presentation are tools for a comprehensive case presentation. Third, case selection is a selection of cases for a given subpopulation. Four, documentation. Documentation is a tool for image annotation, text, and voice reports. 5. Image arrangement or hanging protocols. These are the tools for arranging and grouping images for easy review. 6. Image reconstruction. These are the tools for various types of image reconstruction for property display. 7. Interpretation. These are the management tools for facilitating the diagnosis.
Tag names and signal naming conventions. Purpose of standardized tag names. A consistent naming convention should be developed for assigning descriptive tag names to all of the points in the supervisory control and data acquisition or the SCADA software. Points affected are the first, hardware input and output field signals. Second, interval virtual program points in the Programmable Process Controller or the PPC software. Third, database points used in the SCADA operations workstations or the SOW display and software. Workplace design. Workplace design refers to the process of designing and organizing a workplace to optimize worker performance and safety. It is an important health and safety issues for workers in both high-risk environments and low. Major categories of workstations in the process workplace. First is the seated workstations. It requires the operator to be seated at a panel or at a desk to perform his or her task. Issues with seated workstations are lack of adjustability to the wide range of body sizes that occupy the workstations. Access to the areas that support seated such as filing, storage, binders, communication, and computer equipment. Communication with other seated operators, the design of the operator's chair, and difficult to lift objects or apply force. Second, standing workstations. It requires the operator to stand at a workstation display panel or bench to perform a task. Issues with standing workstations are fatigue caused by long periods of standing, access to tools, materials, and equipment needed to perform the task, height adjustability of the work surface with regard to both the stature of the user and the type of task being performed. Lastly, sit and stand workstations. Sit and stand workstations are used when some of the tasks are done standing and other done sitting. This category offers users the best of all worlds since they do not suffer the fatigue found in standing, yet have more range of motion than seated workstations would offer. The third is sit and stand workstations. Sit and stand workstations are used when some of the tasks are done standing and others done sitting. This category offers users the best of all worlds since they do not suffer the fatigue found in standing workstations, yet have more range of motion than seated workstations would offer.
Before I start discussing 2D and 3D displaying algorithms, let me share to you a brief information about computer graphics. Computer graphics embraces a broad spectrum of topics, including such things as image processing, photo editing, a myriad types of games, and of course, special effects for movies and televisions. Even a word processor or presentation package could be said to fall into this category of graphics program. 2D and 3D displaying algorithms. Let's start with 2D displaying algorithms. Drawing lines in real life is easy as blinking an eye. But drawing lines in computer takes a lot of knowledge and uses certain formula and certain methods. I'll be discussing basic and easy to learn equation, which is the line drawing algorithm. Line drawing algorithm. In computer graphics, a line drawing algorithm is an algorithm for approximating a line segment on discrete graphical media, such as pixel-based display and printers. On such media, line drawing requires an approximation. Basic algorithm rasterizes line in one color. A better representation with multiple color gradations requires an advanced process and spatial anti-aliasing. I know you can recall the slope-intercept form of the following equation. A line y equals the slope m multiplied by x added to the y-intercept b. Given any 2 points on a line, we could find the values of m and b. To find them, we divide the rise by the run, where the rise and run are respectively the differences between the two y values and the two x values of the 2 points. So once we have m, we can substitute the x and y values of either of our 2 points into the equation. And solving for b. So here is an example. Points 10, 20, and 50, 80. So the slope is 80 minus 20 over 50 minus 10, which is 1.5. Then we substitute the x, y values, 10 and 20. Then we solve for b. We get 5, so the slope-intercept equation of this line is y is equal to 1.5x plus 5. For our line algorithm, we have to distinguish between two cases. When the slope is between -1 and 1, it runs more horizontal than vertical. So while every pixel has a unique x value, some adjacent pixels share the same y value, but when the slope is greater than 1 or less than -1, it runs more vertical than horizontal. First picture tells that the line is going horizontal, so the slope is between -1 and 1, and the second is vertically, so the slope is greater than 1 or less than -1. So while every pixel has a unique y value, some adjacent pixels share the same x value. There's actually a third case where the slope is equal to 1 or -1, in which case the line runs perfectly diagonal, such that each pixel of the line has both a unique x and unique y value for our purposes. So we will not be tackling the third case because it will be a very long topic. So let's proceed to 3D displaying algorithms. So 3D visualization presented are more difficult problem. Data that is obtained in 3D usually needs to be converted to an alternative geometric form in order to send it to the usual or to the rendering part of the pipeline. A coordinate system provides a numerical frame of reference for the 3D universe in which we will develop our ideas and algorithms. Two coordinate systems are particularly useful to us. The ubiquitous Cartesian XYZ, the rectilinear system, and the spherical polar or the angular system. So Cartesian coordinates are the most commonly used, but angular coordinates are particularly helpful when it comes to directing 3D animations, where it is not only important to say where something is located, but also in which direction it is looking or moving. So in figure 2.1, it illustrates the Cartesian system. Any point P is uniquely specified by a triple of numbers. We have A, B, and C. Mutually perpendicular coordinate axes are conventionally located or labeled X, Y, and Z. So for the point P, the numbers A, B, and C can be thought of as distances we need to move in order to travel from the origin of point P. In the Cartesian system, the axis can be oriented in either a left or right-handed sense. So a right-handed conversion or convention is consistent with the vector cross product, and all algorithms and formulae used assume a right-handed convention. So figure 2.2 shows the conventional spherical polar coordinate system in relation to the Cartesian axis. So r is a measure of the distance from the origin to a point in space. The angles theta and the empty set are taken relative to the z and r axis, respectively. So unlike the Cartesian x, y, and z values, which all take the same units, spherical polar coordinates use both distance and angle measures. Importantly, there are some points in space that do not have a unique one-to-one relationship with an r, theta, and the empty space or empty set coordinate value. For example, points on the positive x-axis can have any value of empty set. So we have example 100, 0, and pi. So both represent the same point. Also, the range of values which r, theta, and empty set can take is limited. The radial distance of theta takes values to 0 is greater than or equal to theta and is less than or greater to 2 pi. So there is no unique way to specify a range of numbers for theta. One could equally well choose negative pi is greater than or equal to theta but greater than pi. But to avoid confusion, it is best to adhere rigidly to one interval. It is quite straightforward to change from one coordinate system to the other. So when the point is P, in the figure 2.2, is expressed as r, theta, empty set, the Cartesian coordinates x, y, and z are given by the trigonometric expressions. So we have x is equal to r sine theta cosine empty set. And for y, we have r sine theta sine empty set. And for z, we have r cosine theta. Let's proceed to 3D volume rendering. So in scientific visualization and computer graphics, volume rendering is a set of techniques used to display a 2D projection of a 3D discretely sampled data set, typically a 3D scalar field. A typical 3D data set is a group of 2D slice images acquired by a CT scan, MRI, or micro CT scanner. Usually, these are acquired in regular pattern. Example for it is one slice every millimeter. So, and usually have a regular number of images, pixels in a regular pattern. This is an example of a regular volumetric grid, with each volume element or voxel represented by a single value that is obtained by sampling the immediate area surrounding the voxel. To render a 2D projection of a 3D dataset, one first needs to define a camera in space relative to the volume. Also, one needs to define the opticality or the opacity and color of every voxel. This is usually defined using our RGBA. We have red, green, blue, and alpha. So transfer function that defines the RGBA value for every possible voxel value. For example, a volume may be viewed by extracting surfaces of equal values from the volume of rendering them as a polygonal meshes, or by rendering the volume of directly as a block of data. The marching cubes algorithm is a common technique of extracting isosurfaces from volume data. Direct volume rendering is a computational intensive task that may be performed in several ways.
Good day everyone, this is Mary Antonette as Vargas, and for today I will be reporting about ray tracing and virtual reality technology. So, ray tracing is a technique for rendering three-dimensional graphics with very complex light interaction. This means you can create pictures full of mirrors, transparent surfaces and shadow with stunning results. Ray tracing is a very simple method to both understand and implement. It is based on the idea that you can model reflection and refraction by recursively following the path that light takes as it bounces through an environment. So next we have here the ray tracing model. So this is the ray tracing model. We have the camera or the eye, the image, the light source, the scene object, and we can also see the shadow rays. Next is the ray tracing algorithm. So ray tracing algorithm builds the image pixel by pixel. So ray tracing algorithm casts additional rays from the hit point to determine the pixel colors. Then, recursive ray tracing. Recursion is a means of obtaining a result in which a given process repeats itself in arbitrary number of times. Often, the basic ray tracing algorithm is called recursive algorithm. So, when a reflected or a refraction ray hits a surface, these are the processes to be repeated. First is to send more out shadow rays, send out new reflected rays, send out a new refracted ray, generally reduce the weight of each additional ray when computing the contribution to the surface color. Then, stop when the contribution from a ray is too small to notice or maximum recursion level has been reached. So next we have here the Rt3. So as we can see in the diagram, there are several letters. Each letter that can be seen in the diagram represents something. So the letter N represents surface normal, R for reflected ray, L for shadow ray, and letter T for transmitted or refracted ray. So we have here some examples of ray traced images. As we can observe, it is full of mirrors, transparent surfaces, and shadows, which makes the image stunning. So let us move on to the next topic, which is virtual reality technology. So in this area, we will be discussing on what is virtual reality, its history, different types of virtual reality, its hardwares, and the application of virtual reality in our lives. So first, let us talk about what is virtual reality. Virtual reality is a term used for computer-generated 3D environments that allow users to enter and interact with alternate realities. The definition of virtual is near, and reality is what we experience as humans. So basically, virtual reality together means feeling the imaginary or virtual world rather than the real one. The imaginary world is a simulation running in a computer. So in the history of virtual reality, there are more than one person has been involved in the development of this technological system. Virtual reality technology was invented in the year 1957 by Martin Heilig. This multimedia device called the Sensorama is considered one of the earliest virtual reality systems. However, the term virtual reality was coined much later in the year 1987 by researcher J. Lanier. So this image beside shows the timeline of development history of virtual reality from the year 1935 down to 2018. Funny how it works, virtual reality come a long way in the last 50 years but still considered an emerging technology today. So next we will be tackling about the different types of VR. Actually, we have 3 types of VR. The immersive, the non-immersive, and the window on world virtual reality. So first is the immersive virtual reality, the perception of being physically present in a non-physical world. So elements of virtual environment that increase the immersiveness of the experience includes the continuity of surroundings, conformance to human vision, freedom of movement, physical interaction, and physical feedback. This also uses tools that connects to the human body in order to perform the same motor task. Then, the second is the non-immersive VR. Large display but doesn't surround the user. So, in the second type of VR, it allows interacting with the environment through moves and joysticks. And lastly, the window on world virtual reality. It is a desktop-based virtual reality. It involves displaying a 3-dimensional virtual on regular desktop display without the use of any specialized movement tracking environment. So let us move on to virtual reality's hardware devices. We have here 2 types of them, the input and the output devices. So here are some examples of input devices. These are the Prio VR, Razer, Hydra, Leap Motion, STEM, Magic Wand, and Control VR. These devices helps user to navigate and interact with a virtual reality environment to make it natural as possible. Then on the other hand, we also have here the output devices such as the headset, the 3D audio, the sensing gloves, and the Hasten key. These devices stimulate a sense organ. These include visual, auditory, or haptic displays. So let us talk about application of virtual reality. So virtual reality has been used in different aspects of life such as in military training, education, science visualization, entertainment, and the healthcare. So VR is used in military training since it can immerse user in a virtual yet safe world. VR are also used in sports or cinemas, especially in gaming for entertainment. VR is indeed used in all aspects of our life, but today, let us focus on virtual reality in healthcare. So in healthcare, virtual reality is used in medical training, patient treatment, and disease awareness. Medical training. Virtual reality has the ability to transport you inside the human body to access and view areas that otherwise would be impossible to reach. In VR, you can view minute detail of any part of the human body in stunning 360-degree CGI reconstruction and create training scenarios which replicate common surgical procedures. Medical Realities is one of the companies pioneering the use of virtual reality to deliver high-quality surgical training. Medical students using virtual reality can now explore accurate and real human anatomy, including the organ system, in a completely immersive environment. So next is VR in patient treatment. The ability to view the inside of human body in virtual reality is not only useful for doctors but also for patients. The result, enhanced understanding of the treatment and consequently higher patient satisfaction. So in patient treatment under mental health and psychological therapy, virtual reality's unique ability to transport you somewhere else can be used to create powerful simulation of the scenarios in which psychological difficulties occur. The in-situ coaching that is so effective for so many disorders can now be delivered in the consulting room, with the simulation graded in difficulty and repeated as often as necessary. So the image here shows the treatment of a psychological disorder, which is phobia. The therapist here uses virtual reality to his patient in guiding her overcome her fears. Virtual reality's healing capabilities aren't just limited to psychological issues, but have been proved to work for pain management and physical therapy. VR for physical therapy has also been shown to be effective in speeding up recovery time, allowing the patient to do their prescribed daily exercise in a virtual environment makes the activity more fun and keeps the patient focused. So the image here is an example of virtual reality being used in physical therapy and pain management. And lastly, we have here virtual reality being used for disease awareness. Virtual reality helps a lot of disease awareness to the public. An example of that is the pharmaceutical research and development company AbbVie created an experience to raise awareness among healthcare professionals of the daily struggle of patients suffering from Parkinson's disease. Parkinson's is a progressive neurological condition. This means that it causes problems in the brain and gets worse over time. The experience was demoed at a pharmaceutical industry trade shows where people could put on a headset and experience firsthand as a Parkinson's sufferer navigates a virtual supermarket, encountering awkward moments when coming into contact with other people. Virtual reality makes it easier for the user to easily comprehend what type of issue patients face in their lives and how others can